So, without further ado, welcome. My name's Andrew Curran. I'm, as I say, the Director of Science and Chief Scientific Advisor for HSE. It is a great pleasure to welcome you to the launch of our 2023 Annual Science Review. We've structured our Science Review this year around the strategic objectives in HSE's strategy, Protecting People and Places, which is available on our website. And hopefully the turbo talks that you're going to hear today will give you a bit of a flavour as to the evidence that we're providing to support policy and regulatory activity and decision making in those important strategic areas for us. I'm very keen that we make a start because you want to hear from the presenters and not from me. So it's a great pleasure to introduce Jonathan, who is joining us via the medium of video, and he's going to talk to us about the safe deployment of lithium-ion batteries for storage and use of net zero energy. So if I can ask my colleagues to press the play button, and Jonathan will tell us all about this work. Thank you very much.
Hello, I'm Jonathan Buston from HSE's Science and Research Centre, and I want to talk to you about a project we did about the safety of lithium-ion batteries, the Libris project. Now, I'm not going to be able to give you an in-depth experience about the whole project. That took an 18 months to do, funded by the UK government as part of the Innovate Faraday Battery Challenge, and involved a consortium of partners from across the battery chain, and you can see them listed there at the bottom of the screen. But I want just to give you a couple of highlights about things that we did within that project that will give you a flavour of what was going on. And this all involved using the facilities and the skills that we have up in here in Buston, based on our large site, to do abuse testing of batteries. Now, abuse testing is where we're taking them beyond, in some way, what the manufacturer says that they are safe to do. So we're seeing what happens when you push those boundaries. So one example of the work we did within that project with a partner is with Triwall, and Triwall make packaging solutions, and they developed a battery packaging solution within the UK, and we did the testing of that, filling it up with batteries, setting the batteries in the appropriate way so they were going to fail, and showing that the packaging contained that event adequately. Another example is working with Jaguar Land Rover as one of the vehicle manufacturers and designers in the UK. Now, nowadays with an electric vehicle, you do a test where you have to fail one of the cells in the vehicle and show what happens, show how the event is being controlled. And vehicle OEMs are working hard to control those events and to minimize the output and to stop it as early as they can. So like all other partners, Jaguar Land Rover were working on that. They were developing some solutions. We were doing the testing of that to show that their solutions were making a real difference. And I haven't got time to go into the details of that, but yes, they did. And another example is looking at the data needed to do computational modelling. The model is only ever going to be as good as the data that feeds it, that generates it. So we were generating a lot of data and feeding that to a partner within the consortium who was doing that modelling, and there's just a few papers that come out of that. Now, in addition to that work, we were doing some research that we were driving. One strand of that was looking at the gas coming off cells when they fail. So you see on the side of the picture there the rig in which we're generating that gas. That's a sealed system, and it's a system we could fill either with air or with nitrogen. So we're setting up and doing two sets of tests for everything, and you see the results in red there show you get one set of gas composition coming out when you run in air, and the results above in blue show you get a different set of gas composition coming out when you suppress the ability for the thing to catch fire. So those results have been put out, and if you're interested, you can find them in the paper that's referenced in the Science Review. And another little bit of work we did looked at some of the projectiles that come out. Now, we'd noticed that on occasions when cells fail, or we caused cells to fail, they could fly off. Now, that's an uncommon thing, but when they did, it could be quite vigorous. So we followed that through, and here's an example of what that looked like. Now, we're deliberately putting the cell in a flame and holding it in a way that maximizes the chance of it flying, and showing that as a high-speed side-on image now. So this is a slow motion of what the event that you've just seen. And you can see that the cell spins off on its axis. It's a bit like a Catherine wheel as it flies, and eventually hits the far end of the bunker and crumples. Another similar example, but this time the cell flew straight and achieved far higher speed. And I think we clocked that one at just over 100 miles an hour. So it's a significant event. And we took that open field to see how far these cells would fly. This is an example that is not quite so easy to see the cell flying. You see it's flying across the screen at the moment and just landing now. And we're seeing the cells were flying about 30 meters in that example. But this is early work and we need to look into that a little bit more. So just to wind up, I just want to thank the team of folk here at the Science Research Centre that did the work. You can see their photographs there. Innovate generated the funding for that as part of the Faraday Battery Challenge. And the consortium there, it was a really good consortium to work with. We tackled a whole wide range of issues and it was really good working together with that team. So hopefully that just gives you a snapshot of one project that we've been doing in this area. Thank you.
Thanks very much indeed, Jonathan, and some very visual demonstrations of some of the things that we're interested in exploring under this programme. We're now going to move on to Wayne Rattigan from our Explosive Atmospheres team in Science Division. And again, I think Wayne is going to be presenting via the medium of video. Hopefully we'll be able to see that video now. So Wayne, thanks for recording this for us. And if we can play that, that would be great. Thank you.
Good afternoon. My name is Wayne Rattigan and I am a principal scientist working at HSE Science and Research Centre in Buston. The work I'm presenting today is part of the HyTunnel project, whose principal aim was to provide an evidence base to underpin the safe utilisation of hydrogen vehicles inside tunnels and other confined spaces. The use of hydrogen as a fuel in the transport sector has the potential to contribute to delivering the UK's net zero targets. To ensure that current safety levels are maintained, it is important to have scientific evidence on the challenges posed by hydrogen fuel vehicles. HC scientists were part of the 3-year project which carried out research aimed towards the safe use of these vehicles through tunnels and in other confined spaces. The project brought together 13 partners from across the UK and Europe, including researchers, emergency service specialists and standards development organisations. And the aim of the work carried out by HC researchers was to undertake large-scale experiments which would simulate potential real-world accident scenarios involving hydrogen fuel vehicles, providing physical evidence and data which can be used to validate and develop existing computer and engineering models. The experiments included the release of hydrogen inside HSE's 70-metre long, 3.7 metre diameter steel tunnel, an image of which you can see on the lower right-hand side of the screen. Some of these experiments simulated the activation of a thermal pressure relief device, which is fitted to the hydrogen storage system of all hydrogen-fueled vehicles. These devices are designed to activate if the vehicle is involved in a fire and prevent the tanks from bursting by releasing the high-pressure hydrogen in a controlled manner. However, if these activate inside a tunnel, it can cause a potential hazard when the released hydrogen mixes with air and creates a flammable cloud inside the tunnel. These experiments allowed the scientists to understand how large these flammable clouds could become, but also how the hazard could be reduced by studying the effect of different tunnel ventilation rates and different release rates of hydrogen from the pressure relief device. A further set of experiments were also undertaken using the same release parameters, but this time with an attempt to ignite the generated flammable cloud at different times. And this helped us to understand the probability of ignition of the hydrogen air clouds and the potential consequence when ignition did occur. For these tests, we measured pressure at several locations inside the tunnel and used 45 thermocouples to determine how far and how fast the flame travelled inside the tunnel. The findings from the project are extensive, but here is a summary of a selection of the main findings from some of the work carried out by HC. For the unignited releases, the extent of the flammable cloud inside the tunnel was dependent on the size of release and the rate at which it was released. For smaller releases, simulating those from a car, the size of the flammable cloud could be effectively reduced using ventilation rates inside the tunnel of around 3.5 meters per second. Where ignitions were attempted for these smaller releases, it proved difficult to ignite the predicted flammable cloud. In fact, for all the tests attempted, none were ignited. For larger releases, simulating those from buses and trains, and where ignition did occur, the generated overpressure persisted for a long distance inside the tunnel, indicating that an equivalent event in a real-world tunnel would have significant hazard distances associated with it. And just before I move on to the next slide, I just want to show a video from one of the tests. This shows a release of hydrogen from the centre of the tunnel, which ignites, creating a fireball, and the pressure generated from the event causes what looks like a smoke ring at the mouth of the tunnel, but is actually water vapour condensing due to the pressure change. And this 10-second video clip was shot in high speed and actually equates to around 125 milliseconds in real time. So, in summary, the findings of the HyTunnel project closed some knowledge gaps and will pave the way for the development of novel prevention and mitigation strategies by stakeholders following a safety by design approach. HC carried out 57 experiments inside its tunnel facility, and the data produced, including videos from the experiments and other project partner experiments, is freely available from anyone interested on the Zenodo data hosting website. In total, there were 7 work packages, and the deliverable reports from each, including the 3 experimental work packages and the recommendations for the development of regulations, codes and standards, are freely available from the project website. That's the end of my presentation. Thank you for listening.
Thanks very much, Wayne, and I know Wayne will be joining us for the Q&A session. So if you do have any questions, please do type them into that Q&A tab at the top of your screen. So that was a couple of presentations around our strategic objective to support safe innovation in the delivery of net zero. We're going to move on now to some of the work that has been delivered to help reduce work-related ill health, starting with some work that Yiqun Chen will talk to us about, specifically around the national core study that we led, looking at the transmission of SARS-CoV-2 to support the UK response to the pandemic. So Yiqun, over to you. Thank you very much. You're on mute, Yiqun, so you might want to. There we go. Perfect.
Thank you, Andrew. I'm principal epidemiologist from HSC. Within PROTECT COVID-19 National Core Study, I led outbreak investigations. Today, I'm going to present our work as a way to highlight the research and legacy of PROTECT. PROTECT is a strategic national program of work that informs policy and operations to support immediate pandemic response, as well as for future preparedness. PROTECT has 6 themes led by HSC Chief Scientific Advisor, Professor Andrew Curran, and delivered by more than 200 researchers from 16 institutions across the UK, including HSC. HSC led Theme 1, the workplace outbreak investigations, to understand risk factors for outbreaks, control measures, as well as their effectiveness. We brought together very quickly more than 45 scientists from 5 institutions to deliver a very large program of work, including rapid on-the-ground investigations of 20 outbreak sites and comprehensive analysis of national outbreak data. The level of collaborations and data sharing were unseen before the pandemic. The analysis of national outbreak data has consistently identified high-risk sectors, including education, health, public services, food manufacturing and warehousing. Our systematic literature review has showed complex interplay risk factors contributed to workplace outbreaks, and this was backed by our own outbreak studies. The analysis of large linked data set has shown that people living in deprived areas, traveling to work as a passenger and working in close proximities with others were associated with increased risk of workplace outbreak, while having vaccination and permanent contracts reduced the risk. Our on-the-ground investigation has shown it was challenging to maintain physical distancing all the time. People didn't understand ventilation, and we frequently find poorly ventilated areas. The overall level of surface contamination was low. But every outbreak site was different, and it is important to carry out site-specific risk assessments and to implement multi-layer control measures. We were able to be innovative. For example, we link national outbreak data with business register to calculate outbreak rate. It's the way to identify high-risk workplaces, and this approach was adopted by UK Health Security Agency. We were able to detect COVID-19 clusters as detailed as at individual building level, which advanced infectious disease detection and analysis not limited to COVID. We link national data set, including NHS contact tracing data, vaccination data, and census data to investigate more holistically the risk factors for workplace outbreaks. So we can consider the characteristic of the workplace, the workforce, the local infections related to where people live, where people work, and the way they travel to work. This approach will benefit wider health research and not limited to COVID. Our workplace outbreak investigation is comprehensive and systematic, which is quite unique in the world. We're going to update our study protocol based on the lessons learned, so it can be readily deployed for future pandemic. Our work has contributed to the global evidence of virus transmission and control in the workplace. The new way of working and methods developed can be applied to wider workplace health research. It also highlights one of the key Protect legacies, which is to provide UK with the capability for rapid response to future pandemic threats. Thank you.
Thank you very much indeed, Yiqun. Really, really important work, and great to see this moving out into the post-COVID world. Moving on to a second COVID-related presentation now from Claire Bailey, who's going to tell us about how some of the decontamination interventions might help to control transmission both of SARS-CoV-2 and possibly for future pandemics as well. So Claire, thank you very much, and over to you.
Can everybody hear me now?
Okay, can you see the slides, Claire?
Yes, I can. Can everybody hear me?
Yeah, you might want to move your microphone a little closer, but yeah, looks good.
Okay, well, hello everybody. I'm going to talk about the modern decontamination interventions that may help to control SARS-CoV-2 transmission. In particular, I'm going to talk about air cleaners. So if we move to the next slide, there we go. So what we're trying to do during this study, there was a lot of talk about using air cleaners to improve ventilation systems, but there was a lack of consistent information regarding the ability of air cleaning technologies to actually remove bioaerosols. And we wanted to look at a couple of different types of air cleaners in a side-by-side comparison, so you can see how effective each one really is compared to another. We appreciate that air cleaning performance is likely to vary but the question is, do they actually work in practice, and could they be used in offices or other closed environments to reduce airborne spread of bacteria and viruses such as SARS-CoV-2? So within the study, we looked at 5 air cleaning devices. Now these come in a variety of shapes and sizes, and also a variety of costs, from quite cheap to very expensive. We picked 5, and we tried to get a selection of what's commercially available, right through from the plug-in devices that you buy off the shelf to more bespoke ones that are designed to be electrically wired into ventilation and aircon systems. The ones we picked all had a filtration system of some kind within them, and in 3 of the cases that filtration system was also combined with a UV decontamination system. We avoided anything that produced a secondary product such as ozone, for the reason that these are designed to be permanently in an office space or a building and run, and we weren't sure if by producing these secondary products we were exposing workers to other hazards day to day. So as you can see from the pictures, the size of them varies quite considerably. So what did we do? We got within HSE, we've got a controlled air chamber, which means we can seal, it's basically a sealed box. We can fill that sealed box with virus. So on the right hand side, you can see the nebulizer, which we filled with virus, and that then fills the room. While the room was being filled, we looked at the final particle concentrations. But over a 3-hour period, once the room was filled and sealed, we took air samples over the 1-hour period, the 2-hour period, and the 3-hour period. We also measured particle sizes, both small and large, to see if the air cleaners were working and were reducing the viral load within the room. So how did they do? All the air cleaners reduced the viral concentration, bioaerosol concentration within the room. The performance did vary, but even the best with the best performing air purification device reducing the concentration below the experimental detection threshold within quite a short space of time. The final challenge that we gave it was extremely high, and we showed that even the worst performing device still demonstrated a measurable reduction in bioaerosol concentration over the 3-hour period. So what does that mean? So in real world scenarios, even the worst performing device could potentially help mitigate or reduce bioaerosol spread and offer benefits for reducing airborne spread of viruses such as SARS-CoV-2. I'd also like to mention that although this work was done under the NCS Protect research project, it also builds on work HSE have previously done looking at air cleaners to remove other airborne particulates such as diesel fumes, and I think that this work plus the work we've done previously suggests that air cleaners do have quite a wide potential to improve building air quality and protect workers. Thank you for listening.
Thanks very much indeed, Claire, and thanks for putting up the reference at the end there as well. Okay, another health project now, and it's a great pleasure to introduce Antonia Hawker, who's going to talk about the work that she's been doing looking at the impact on angle grinders from noise and vibration. So, Antonia, over to you. Thank you very much.
Okay, so I'm going to talk about hand-on vibration and noise emissions of battery-powered tools compared with equivalent traditionally powered tools. Handheld power tools are a source of noise and vibration to which operators are exposed during use. These are hazards because repeated exposure to noise can potentially cause noise-induced hearing loss, while hand-on vibration syndrome is a work-related disease caused by repeated exposure to vibration, and power tools are sources of vibration. Damage from hand-on vibration syndrome can include inability to do fine work, and cold can trigger painful blanching attacks. Both of these conditions are irreversible and can severely limit a person's quality of life. Battery-powered tools are increasingly common in the workplace. Manufacturers have produced information which suggests that some battery-powered tools may be lower in noise and vibration emissions than similar alternatively powered tools. This information may not predict the actual in-use exposure to noise and vibration when using these tools as designed, giving rise to concerns about the risk of workers developing hand-on vibration syndrome and noise-induced hearing loss. The aim of this research was to further understand noise and vibration levels from battery-powered handheld tools compared to traditionally powered equivalents, such as electric, pneumatic, or combustion, by undertaking tests on a representative selection of battery-powered tools and traditionally powered equivalents. So for each machine type identified for investigation, we approached one major manufacturer and worked with them to identify suitable machines of battery and other power sources for comparative testing. The tools that were used in these tests were chainsaws, cut-off saws, angle grinders, combi drills, impact wrenches, and reciprocating saws. For each tool, we had a battery version and then either an electric, pneumatic, or combustion-powered version that had an equivalent power rating. We then carried out controlled in-use tests of the noise and vibration emissions from these machines and used them how we would expect them to be used in industry. We also considered what factors specific to battery power technology could influence the measured noise and vibration. For example, what happens to the power of the tool when the battery begins to discharge. We then directly compared the noise and vibration emission data for the battery-powered machines with the data for traditionally powered machines. So the positive findings. The sample battery-powered chainsaws, reciprocating saws, and drills when used drilling into metal used in these tests consistently produced lower in-use noise and vibration levels than the sample equivalent petrol or mains-powered machines. Additionally, the in-use values were similar to the manufacturer's declared values in instruction manuals. For all other machine comparisons, there were factors other than the power source which could dominate differences in noise and vibration emissions. There was no assured reduction in noise or vibration from choosing battery-powered over traditionally powered machines. The battery-powered tools may therefore be lower in noise or vibration for some activities undertaken, but the traditionally powered tools could be lower in emissions for other activities. Similarly, the choice of consumables, such as the wheel or drill bit used, can have a greater influence on emission than the power source. For example, with the angle grinders, the mounting of the wheels and the consistency in the makeup of the wheels influence noise and/or vibration emissions. In-use testing also showed significant differences between emission values declared in instruction manuals and those measured during use. What is very important to note are that these are the findings for these particular makes and models and may not be consistent for all models. So take-home messages. Battery-powered tools cannot be considered lower in noise and vibration emission for all tools. There are factors other than the power source which could dominate differences in noise and vibration emissions. There was no assured reduction in noise or vibration from choosing battery-powered over traditionally powered machines. It is important that duty holders identify efficient tools that are appropriate for the job regardless of the power source, avoiding any high noise or vibration models, and then manage the remaining noise or vibration risk. So in summary, do consider battery-powered tools if they can do the job appropriately and efficiently. Do look at noise and vibration emission levels stated in the instruction manuals, but treat them with some caution. Do not assume that battery-powered tools will be lower in noise and vibration emission for all tools. Thank you for listening.
Thanks very much indeed, Antonia. Really interesting and helpful advice there. Okay, we're going to move into another area of our strategy now, which is making sure we increase and maintain trust to ensure people feel safe where they live, where they work, and in their environment. And it's a great pleasure to welcome Bryn Bircher from our Chemicals Regulation Division to tell us about some work that's being done to look at the use of drones to assess pesticide applications. So, Bryn, thank you very much for joining us, and over to you.
Thank you very much, Andrew. Where are we? Thank you very much, Andrew. My presentation, as Andrew said, is about the authorisation of the first UK application of pesticide using a drone. It's a team effort from people from Health and Safety Executive's Chemical Regulation Division. The application of pesticides by drone or remotely piloted aerial systems has generated a lot of interest over the last 5 years. And the interest has come from CRD's usual stakeholders, chemical companies, farmers and growers, but interest has also come from a new set of stakeholders, drone operating companies who see the ability to apply pesticides by drone as a new business opportunity. So Network Rail is responsible for over 30,000 bridges, tunnels and viaducts, and many of these require vegetation to be cleared on a regular basis. This has often been carried out by rope access workers working at height, often during the hours of darkness and under time pressure whilst the railway lines are closed. The workers need to carry equipment, and if applying herbicides, they'll be wearing a knapsack or backpack sprayers, which makes the work more dangerous and not particularly efficient. For a number of years, Railscape have been developing a method of applying herbicides to railway infrastructure whilst removing the risks of working at height in the dark using artificial lighting in a restrictive area. Working on the railway, as I've already said, is often limited to short periods of time when the track is closed, adding additional pressures to work efficiently. Railscape understand the challenges of working on the railway. They partnered with a drone company and approached HSE CRD to discuss the possibility of applying pesticides using a drone. Drones were already on our radar when we were approached, and we were keen to support this activity. CRD specialist scientists provided detailed advice and guidance on the data that would be required for later evaluation. The Railscape engineers designed and developed and tested a fully functional method of applying liquids in a precision manner to vegetation at height or in difficult to access areas. Railscape introduced CRD to Harper Adams University so HSE specialist scientists could provide the necessary advice and guidance to the university before they started carrying out the trials to produce the data that would support the application to apply a herbicide using a drone. HSE specialist scientists also provided extensive support to Harper Adams University to ensure that the data being collected was sufficient for regulatory purposes. Once the trials were complete and the data were provided for application for authorization, specialist scientists carried out a full regulatory evaluation to confirm the risks of spraying pesticides from the Railscape drone was within the limits set for other application equipment. The CRD evaluation established that herbicides can be applied using remotely piloted aerial systems or drones directly to the target plant without the requirement for rope access or height access equipment. The spraying operations were carried out during the night towards the end of the summer in 2022. A follow-up visit showed that the spraying operation had been successful and that the vegetation was drying off. In addition to the obvious safety advantages and risk removal the new application method presents, the operation is precise in targeting, precise in delivery, and will use considerably less pesticide with less risk of spillage. The work resulted in the first authorization for an application of a herbicide by drone in the UK. CRD will build on this information and experience gathered from the evaluation of this application to support additional UK and international work to make the application of pesticide by drones more commonplace. Thank you very much for your attention.
Thanks very much indeed, Bryn. Really interesting and novel application of drone technologies. Let's move on to Mike Hemingway, and Mike's going to talk to us about some work we've been doing and again the strategic objective to maintain GB's record as one of the safest countries to work in. And Mike's going to talk about some investigation work that we've been doing to understand the sad and upsetting fatal consequences of the misuse of a flammable gas monitor. So Mike, over to you. Thank you.
Hello, everybody. Thank you, Andrew. Yes, I'm going to be talking about HSE's investigation into the fatal consequences of the misuse of a flammable gas monitor. Back in 2018, there was an explosion at Briar Chemicals that killed a welder who was carrying out maintenance work on a mixing vessel. The mixing vessel was supposed to have been emptied, but a fault in the system allowed toluene to leak into the vessel. The incident should have been prevented because the vessel had previously been tested by flammable gas monitors, which unfortunately didn't pick up the toluene vapour inside the vessels. The investigating inspectors wanted to understand why the gas monitor didn't successfully measure the flammable gas. This was only a small part of the total HSE's investigation into the whole incident. So the objectives, as far as we were concerned, was to determine the settings and the conditions of the gas monitor on the day of the incident, to use these settings to test the various monitors in the laboratory against known concentrations of toluene gas. And you can see here, this is a picture of the actual gas monitor that was involved in the situation. It's a fairly standard personal gas monitor that can monitor oxygen, carbon monoxide, hydrogen sulfide, and of course, flammable gases. The sensors are within the main body of the monitor, and there's a small pump which can draw air through a sampling tube, which can be placed into a vessel or other areas of interest to draw a sample. The gas monitors were tested in the HFE standard atmosphere test facility, and you can see a picture of that down on the bottom left. We have a system of generating vapours and gases, which can be then inserted into a glass sampling chamber, and then we've got here three various gas monitors which are connected to the sampling chamber, so that each monitor is exposed to exactly the same concentration and gas all the time. Using this apparatus, we were able to measure the effects of different gases, different concentrations, different sampling tubes and lengths, different gas sensors, and the different calibrated monitors. So the main findings, there were a number of findings, but these were the most significant, was that the wrong sampling tube material was used, which slowed the toluene reaching the gas monitor. So specifically, the gas monitor would take 7 minutes to alarm on exposure to toluene, but less than 2 seconds on exposure to methane. This is because toluene, amongst other gases, is effectively a sticky chemical that is readily absorbed onto the inside surface of the sampling tube. Once a coat of hydrogen sulfide of toluene had been built up on the inside surface, then the toluene could break through to the gas sensor. The next significant effect was that the gas sensor was fitted with a filter, which is designed to improve the response of the filter to alkanes such as methane and propane by filtering out volatile organic carbons, you guessed it, such as toluene. Finally, although all flammable gas sensors are responsive to all flammable gases, they are only accurate when measuring one to which they'd been calibrated. And in this case, it was the gas monitor being calibrated with methane, which meant that it would indicate only 34% of the actual concentration of toluene. So all these factors resulted in the gas monitor being very slow to respond, and when it did finally respond, having a much reduced response. So the results of the work was a successful prosecution of Briar Chemicals. We also had a HSE safety alert issued, which will help to prevent this happening again in the future. And the take-home lessons are that gas detection is not always simple. If you have a safety critical need for gas detection, you need to educate yourself, and most importantly of all, bump test. What this means is just do a performance test of the gas monitor to make sure it's working every time you need it. If the users of the gas monitor had just inserted the end of the sampling tube into headspace of a jar of toluene, for example, this would have shown no response on the gas monitor, and they would have known there would have been a problem. And that's the end of my presentation. Thank you.
Thanks very much indeed, Mike. Some important learning from that very sad and tragic incident, and yes, lots to think about there.